Okay, to finish this block, we have the presentation from Demián García-Violini from Universidad Nacional de Quilmes y CONICET, and it's called Control Co-Design of Wave Energy Converters and Technologies. All yours.
So, thanks for the introduction. I'll present this work that I am okay here for the thanks. I'll present this work that I have presented last week in RPIC, in the Control and Signal Processing Conference that the control community hold every 2 years. So for those there, sorry, anything new. So as we know, and I guess that's why we are today here, ocean waves hold vast untapped energy potential, and in order to obtain and harness this power, this energy available there, control systems are essential. And I would like to make a stop here. If we can agree with these 2 points at the end of this workshop, it will be a success. So, and Argentina has historically delayed the exploration of wave energy system in comparison with, for example, wind and solar. We have some experience with solar and wind. Actually, we have good resources, mainly for wind, but no exploration is, in deep for wave energy system, for marine energy system in general. So, but nowadays, initiatives like REMA, ENAEM, this workshop of course, and FONARSEC-funded projects are raising awareness within the academia, within the industry, and mainly within the government. As I remember Sean's first talk, politics here is quite instrumental to move forward. So my presentation is about a control co-design implementation. So control co-design is an innovative approach that integrates the control strategy design into a global perspective of designing. Okay, control co-design offers a more holistic approach than traditional method that in general propose fragmented approaches that may not lead to an overall optimal design. I have here 2 references. The first one is by Mario García-Sanz. Mario García-Sanz is a Spanish researcher who leads the ARPA-E project in the US. And this paper here is a quite interesting paper because discusses in deep very right there. So that paper discusses in deep the very several actions regarding control co-design. And in addition, I want to mention that control co-design has been included in the roadmap 2030 by the IEEE Control System Society as one of the methods in order to approach the new challenges we have for energy systems right now. So control co-design is an instrumental perspective for designing controllers to tackle and address new challenges in energy in general, but particularly in energy systems. Here, we have the traditional sequential unlocking design paradigm. For example, I am focusing here particularly on in wave energy systems, but we can extend this to any other application, for example, wind energy system. So in general, we start with hydrodynamics. We take NEMO, we compute the hydrodynamical parameters, then we say, okay, this is the hydrodynamic, we know the efforts that the system will experience, so we move to the mechanical structural design of the system, then we move to the electrical design, then we move to electronics, and finally we say, okay, we have this system, we need a controller for this system. So that's very, very locking because we are extremely fixed to the structure that we have designed. In contrast, on the contrary, control co-design suggests to take all the particular subsystem that we have and we study in a global perspective the interactions between all these subsystems. So, for example, we introduced at the very beginning the control engineering, the control design part, and we analyze the control design part and its interaction with mechanical engineering, computer science, and particularly with economics and business, and because that's the key point in wave energy system. We have to lower down the levelized cost of energy. So analyzing the interaction between control engineering and economics is a key step in achieving proper and efficient design. And in this paper, Mario Garcia-Sanz suggests this example, okay? At the very beginning, before the age of aviation, before the age of airplanes, all the designs aimed to obtain a more stable design. And to this aim, all the designs suggested, for example, larger wings, more wings, as in this case we have 3 wings. This was in the direction of obtaining more stable designs. But this, I can see some of the faces of my students. So this structural design obtained a more constrained system. We had a very limited bandwidth for control, so that was very limiting. So all the controller couldn't really act on the system in order to get a proper control and stabilize definitely the system. The Wright brothers suggested to move forward to the front, the center of pressure, adding this wing, this wing here at the front. That design structurally was extremely unstable, but this allowed for achieving a more effective controller in terms of bandwidth. We obtained a faster controller, and that was what initiated the age of aviation. Okay, that's allowed. Okay, so we introduced the controller within the structural design of the thing, and we obtained finally something that worked. So this is basically an overview of the big picture, the landscape of control co-design. Introducing the controller at the very beginning of the design and study its interaction with different subsystems. So the foundations of this study is, okay, we need to achieve energy absorption maximization in order to get commercial competitiveness for wave energy systems as a key milestone in the wave. In the way to efficient wave energy systems. We need control methodologies to harvest this energy to maximize power absorption, and in general, in the literature, control systems for wave energy systems are divided into 2 categories: optimization based for control persons here, MPC control, moment matching based control, or spectral controllers, as we use for this study, and non-optimization based controllers, as for example those based on the maximum transfer theorem for those from the electrical field. So in this study, we present a control co-design scheme incorporating both spectral based, including a spectral based controller and a reactive controller, a PI controller, a proportional integral controller. While we explore various structural dimensions and features of the system, okay? And we want to achieve the optimal design considering these circumstances, controllers and dimension structural definitions. We have the standard framework, the standard theoretical framework to deal with wave energy systems. We have and I don't really want you to get all the details in here. I want you to take only the concept, the ideas behind this. So we have the balance of forces. We have the inertial torque, because we are dealing with a rotational system. We have the radiation torque here, which is in essence the dissipation of energy of the system, is the damping action of the system. We have the buoyancy, which is the restoring torque as the spring in a mass damping system. And then we have the external forces. We have the tau x, and we have tau u, which is tau x, the force that the waves are exerting on the system. And we have the external input, the one we use for... there are some colors here. Can you see the colors there? Or no? Okay. So we have it's quite strange this. So we have the external torque here, the one we use to maximize the power absorption. And then we can move this definition from the time domain, okay, to the spectral domain using the standard Ogilvy's relations, which are this we have here. So then we move to the spectral domain. You have here a QR code that you can scan and you can find an experiment for identifying the system, but upstairs there is a poster with a lot of these QR codes with more experiment and explanation and whatever. So we have this definition in the spectral domain, and then we have the control objective maximizing. The control objective is to maximize the power absorption, which is in essence this objective function we have here, and this is the most formal way to define the control problem, the maximization of this integral, which is the multiplication between the system velocity and the control action, subject to the system dynamics, the equation of motion, subject to that the velocity is a combination, and in general we assume a linear combination of the state, and subject to a set of constraints which are general motion constraints, velocity constraints, power, reactive power constraint. Okay, and we have a solution for this problem here, this optimization problem, with no motion constraint, no system constraints in the spectral domain, which is the impedance matching condition. And from this condition here, we can have an optimal mapping between excitation torque and velocity, which is a real mapping, which means that under optimal condition, the external excitation torque is synchronized with the system velocity. Okay, your portion under this optimal condition, the wave is pushing synchronized with the velocity of the system, and that's a good indicator we use to assess control performance. Then we have two control paradigms that we are considering. First one is standard PI controller, which allows for narrow bound energy absorption. We have here equations, but it's a simple controller. Okay, 99% of the controllers worldwide are PI or maybe PAD controllers, and this is the definition. Okay, don't need to get the concept behind the work. You don't need to understand this equation. Simple controller, that's it. And then we have an optimization-based controller in the spectral domain for those coming from a control background. An spectral controller is a controller that discretises in the spectral domain the objective function, and after that we can go from integral differential equation to an analytical vectorial equation, like this one we have here, and this is the consequence. This is the resulting objective function when we simplify using this spectral approximation. Then we obtain a simpler definition. And then we optimize the contour using this spectral simplification. And we can use standard solvers, QP solvers for quadratic programming problems. It's a standard problem. So we start with something tough to solve, which is non-casual, which is, okay, has several analytical limitations, but we can significantly simplify the problem. So we have this system. This is the system that we are considering in order to address this. Are we okay with the time? 5. Okay, perfect. So we have this system. We have this fixed height because we are considering the conditions we have in the onshore, the coast of Mar del Plata, here in 350 kilometers from Buenos Aires. So we have this fixed distance, and we consider the variation of these two parameters: the horizontal distance to the pivot point and the radius of the system. We are going to play with these two variables in order to find an optimal design combining this horizontal distance, the radius of the wave,
keep them fixed this height we have here, the optimization objective, and to the design parameter that minimizes a cost function. So now we have introduced the energy absorption cost objective function. We introduce a new objective function. We have two right now. This one will, for example, can consider the total cost of the system, combining capital cost and the capex and the OPEX, the operational cost, the expenditure, sorry. So we can combine absorb power and total cost, and we can combine, as we are going to do, or something like that in this study, combining the total mass and the absorb power that we have here. Okay? So we are going to try to maximize or minimize, this objective function, substitute the solution of the previous objective function, the one that we generally maximize as a optimal control problem, the energy maximization. So we have two objective functions, okay, and we can tackle this problem as a multi-objective optimal problem or something like that, which is seems to be nice, but it's not always the best way to address this problem. So we have the WEC system. It's a hemispherical bottom. It's a cylindrical shape with a hemispherical bottom. We have these two design variables which define our vector, parameter vector. And then we define a domain in order to search for the solution, which is based on the definition of the horizontal distance as a function of radius. Okay, and this is the domain we end up having. This is kind of triangle in here. So we will look for the solution within this domain here. So then we have the spherical domain, the transfer function of the family of the system, and we have three cases here: 2 meters radius, 2 meters, 5 meters, and 10 meters. And then we vary the horizontal distance, and we obtain a very wide family of models. Okay, and we can see that as long as we increase the horizontal distance, the frequency response goes down, as indicated with this great scale, magnitude, and phase. We, for the control solution, we impose a acquisition constraint of minus plus 30 degrees to preserve realistic rotational motion, to preserve physical integrity of the system, etc. And we assume for the computational solution full knowledge of the wave execution torque. We assume that we know the wave, so we know the wave execution torque. We synthesize waves. We use 10 random realizations in order to achieve statistical consistency. We have here 10 traces. We have here the power spectral density or something like that. Assuming this condition, typical period 10 seconds, typical wave height, 2 meters, and peak engagement factor 3.3, which are what we assume as standard conditions for waves in Mar del Plata, but actually we don't know because we don't have proper information about the waves in the South Atlantic, so that is a lack in the research, in the literature for the field. We have a hole there that we should fulfill quickly. So then we have the objective function that we are trying to minimize. Okay, the optimal case, comparing absorbed power and the mass, and we include an additional term which is proportional to the linear distance from the pivot point to the void. Okay, assuming that as long as we increase that distance, that will impact on the final cost or something like that. We are not using actual data, for example, for cost or maintenance. We are assuming that, this can be closely related to the final cost, because it's a conceptual study that we are proposing here. Then we have the time traces that we obtain we apply these controllers. We have at the top, we have in blue line the wave excitation torque, and we have in red solid and red dashed lines the the control torques we obtained with each controller. Solid line is spectral controller, dashed line is PI controller. We can see that we fulfill ingredients with, I said, 30 degrees. We have the equivalent ingredients. We can see that we are fulfilling always with both controllers, even with the PI, which is not intrinsically designed for handling constraint. We are preserving the constraint. We keep the system within the objective limit, and we can see that the velocity is absolutely synchronized with the execution. If I speak and point this thing, can be really understood. So here we have the optimal absorb power. Okay, we can see that as long as we increase the rate of the system, we increase the absorb power that we can obtain. Of course, we have a limitation which is related to the constraint that we have designed. That's why it's a kind of asymptotic behavior. At some point we achieve the optimal. But when we balance this absorb power with this mass plus factor depending on the linear distance, we can see that the optimal value is in the middle. It's not exactly as long as you increase the radius, you get a better case. No, we have an optimal case in here. This means that in order to approach a global design, okay, assuming that the mass is related to the final cost of the system, maybe this is the optimal case and not stop increasing the radius. Basically, that's the bottom line. So some conclusions. The conclusion that we have here that we are simplifying assumptions. However, we can note that we end up with a very non-linear problem, okay, which is not really simple to approach even with non-standard optimization solvers. The study highlights the importance of utilizing a global optimization criterion because we can see that we include the mass, or maybe we can include the capital cost. We have one paper with John, including analyzing proper costs that we took from the literature. And then, as an important point here, we are assuming a kind of actual conditions for the design in order to put the system on the coast. And finally, of course, and we know a final implementation of the system will need to study anchor, will need to study grid connection, security considerations, couple of stuff. So that's it.
Thank you very much for your good presentation. Is there any question?
You're author of this paper, so
feel obliged. So just going back to the previous presentation that showed a little bit more about the Mar del Plata implementation.
Yes.
So it's likely to be implemented on a key wall or on a break.
Yes, we actually don't know. That's why Claudio's presentation was super instrumental in this because we have a black hole in the legislation. We actually, when we go to the port authority, they say no, we are not the people. You should go to the province authority. Then we go to the police of the sea, and we are turning in circles. We have been turning in circles for the last 2 years. So we don't know. We have a space. We have a couple of potential object target spaces that we can, but we don't know because we don't have a permission. So we are assuming general considerations that maybe we can then adapt easily, but we don't know.
Yeah, I suppose my point is that it will be interesting to see if you included the key wall in hydrodynamic model.
Absolutely.
How that would have changed the optimal parameters.
Absolutely.
Especially the horizontal distance between the hinge and the floor.
Absolutely. Reflection from the wall and actually, you know that there are these big blocks, the beach, which is made with this beach, with very big blocks, stone blocks. That has an impact on with the interaction of the system. So it's not really easy. We don't have information. Nobody wants to design sign a contract, they say, no, I'm not the guy, you should go there. So we have the uncertainty level we are handling with is maybe 1000% or something like that. We are under uncontrolled conditions or something like that.
But you have the whole optimization setup.
Yes.
Right? So and you know, I trivialize this by saying that it just be a case of altering the hydrodynamic model. But you know, given that you have the rest of the setup there, it'd be interesting just to see.
To see the impact that the back wall can have on the city, definitely, yes. Yes.
Thanks. Okay, we are running out of time. Thank you very much, Demián, again, for your presentation.
Thank you.